Internal flows. Laminar flow, hydrodynamic entrance length, laminar flow through circular pipe, laminar flow between two fixed parallel plates, Cotte flow, laminar flow between a fixed and a parallel moving plate. Laminar flow, if the fluid particle in adjacent layer do not mix with each other, then the flow is laminar. In laminar flow, well-defined streamline pattern exists. For a flow through circular pipe, laminar flow is observed when Reynolds number is less than 2000. Re is equal to rho Vd by mu less than 2000. Hydrodynamic entrance length. V1 is equal to V2 is equal to V3, which is average velocity. U infinity is here, U1 less than U2 less than U3. U is here velocity near the boundary, this boundary. Here U is velocity at midpoint. U is velocity at midpoint. Here U at boundary, it is U is equal to 0. Tau entry is equal to mu U infinity by 0 is equal to infinity. Boundary from here to here it is boundary layer growth, from here to here it is profile development, from here a fully developed flow. Boundary layer growth and profile development both combined called as hydrodynamic entrance length. U decreases velocity near to wall in flow direction. Delta y is equal to c. Tau decreases, tau 1 greater than, tau 2 greater than, tau 3. Entrance length is the distance at entrance of pipe in which velocity profile gradually modifies to a well-defined shape. After entrance length there is no change in shape of velocity profile. Such flow is called a fully developed flow. When uniform flow enters into a pipe at surface, no slip condition must be satisfied. Hence, fluid layer near to surface becomes stationary. This layer exerts retarding force on fluid particles in next layer, which slow down gradually. This leads to formation of boundary layers over the surface. Within boundary layer, velocity changes gradually from 0 to maximum, and outside the boundary layer, its central region, velocity is constant at in any layer. The velocity of fluid particle near to the surface decreases gradually in the direction of flow due to viscous force. Hence, velocity at center must increase in order to satisfy conservation of mass. When boundary layer merge, the flow takes some more distance to become completely stabilized. This distance is called profile development length. Velocity gradient at surface is highest at entrance of pipe because velocity increases from 0 to u infinity within negligible distance. In entrance length, the velocity gradient at surface gradually decreases in the direction of flow as velocity decreases due to viscous force, and velocity gradient becomes constant at fully developed flow. The shear stress profile also follows similar trend. In a area from high to keeps on decreasing infinity, it keeps on decreasing till entrance length, and fully developed tau becomes constant. The flow in entrance length is difficult to analyze, hence analysis is done only for fully developed flow. Length of hydrodynamic entrance length is given by LH by D. LH by D is equal to 0.05 RE for laminar flow. LH by D is equal to 4.5 RE power 1 by 6 for turbulent flow. Laminar flow through circular pipe. Laminar flow through circular pipe. Assumption: flow is steady and incompressible. Flow is fully developed, that is, velocity profile does not change in direction of flow. U is equal to U of R. Actual U is equal to U of R comma theta comma x, both same steady tangential. Pressure over any cross section is assumed to be uniform. Pressure over any cross section is assumed to be uniform. P into pi at cross section at dx, consider dx length, P into pi r square, P plus dp by dx into pi r square, tau into 2 pi r dx. Sigma fax is equal to max tends to 0, px pi r square minus of P plus dp by dou x into dx pi r square minus tau into 2 pi r dx is equal to 0. Minus dp pi r square minus 2 pi r dx is equal to 0. Tau is equal to minus dou p by dou x into r by 2. Above equation is valid for both laminar as well as turbulent flows, as same FBD is valid for both flows. Tau W is equal to minus dou p by dou x into capital R by 2. Dp by dx is equal to minus 2W by R is equal to minus constant. Above equation show that pressure gradient is negative constant, hence pressure must decrease linearly with respect to x. Therefore, for flow through horizontal circular pipe, pressure always decreases in direction of steady flow, and that decreases is because of friction. This equation is valid for both laminar and turbulent flow. dp by dx is equal to minus 2 tau w by r pressure. For laminar flow through circular pipe, the shear stress is also given by Newton's law of viscosity. Tau is equal to mu du by dy. In above equation, my negative sign minus mu du by dy. Negative sign introduced because velocity decreases in radially outward direction. This equation is valid only for laminar flow because in turbulent flow, in addition to shear viscous stress and Reynolds stress are also present. For turbulent flow, tau is equal to tau A plus tau R. Okay, for laminar, minus mu du by dr is equal to minus dp by dx into r by 2. Du by dr is equal to dp by dx into r by 2 mu. Integrate with respect to dr is equal to 1 by 2 mu integral dp by dx into r dr plus c. It will be r square, r dr is r square by 2. Finally, u is equal to 1 by 4 mu dp by dx into r square plus c. At r is equal to capital R, u is equal to 0. From that, constant c is minus r square by 4 mu dp by dx. Finally, u is equal to minus 1 by 1 by 4 mu dp by dx small r square minus capital R square. At small r is equal to 0, u is equal to u max is equal to minus r square by 4 mu dp by dx. U is equal to u max into 1 minus small r square by capital R square. Parabolic profile. Average velocity is defined as v is equal to q by a is equal to 1 by a integral 0 to r dq is equal to 1 by pi r square integral 0 to r u into 2 pi r dr. V is equal to 2 by r square integral 0 to r u max into 1 minus small r square by capital R square into r dr. V is equal to 2 u max by capital R square into r square by 2 minus small r power 4 by 4 in 0 to r. V is equal to 2 u max by capital R square into r square by 2 minus r capital R square by 4. V is equal to u max by 2. U max is equal to minus r square by 4 mu dp by dx. dp by dx is equal to minus 4 mu u max by capital R square. P2 minus P1 by x2 minus x1 is equal to minus 4 mu u max by capital R square. Delta P by L is equal to minus 4 mu into 2V by d by 2 whole square. Delta P is equal to 32 mu V L by capital D square. Hagen-Pauli equation. Delta P is equal to P1 minus P2. Pressure drop in direction of flow over length L. All important equations for circular flow. Velocity profile will be like this. Shear stress will be, distribution will be like this. Tau is equal to minus dp by dx into small r by 2 is equal to minus mu du by dr. U is equal to u max into 1 minus small r square by capital R square. V is equal to u max by 2. Delta p is equal to 32 mu v l by d square capital D square. Okay. Problems based on that. The expression the delta p is equal to 32 mu v L by d square is valid only for steady flow. The flow is unsteady as velocity is at any location continuously increased with respect to time, but in question it is mentioned that pseudo steady state can be assumed. Hence, formula of the pressure drop can be used. This is used only for a steady flow. Okay, laminar flow through inclined circular pipe. X take x in this direction at an angle theta, p into pi r square, p plus dou p by dou x into dx into pi r square, tau 2 pi r dx. Sigma fx is equal to mu x. This is 0. Here a special term minus dw into cos theta. It will be in this direction, so minus dw into cos theta. Dw we can write rho g pi r square dx cos theta. Finally, tau is equal to minus dp by dx into small r by 2 minus rho g r cos theta by 2. Tau is equal to minus r by 2 dp by dx plus rho g cos theta. Tau is equal to minus r by 2 dp by dx plus rho g dz by dx. Um, Tau is equal to minus r by 2 d by dx of p plus rho g z. P star is equal to p plus rho g z. Tau is equal to minus r by 2 dp star by dx. P star is equal to p plus rho g z. Tau is equal to minus dp star by dx into r by 2. Above equation shows that formulas of for inclined pipe can be obtained by replacing P by P star in the formulas of horizontal pipe. Tau is equal to minus dou P star by dou x into R by 2 is equal to minus mu du by dr. U is equal to U max into 1 minus small r square by capital R square. V is equal to U max by 2. Delta P star is equal to 32 mu VL by d square. Formula for inclined circular pipe. Laminar flow between two fixed parallel plates. Fixed parallel plates, height h, this is y, this is h minus y, total height h, l length b. Assumptions: size of plate is very large as compared to depth, h less than b, comma l. Therefore, variation in velocity profile and jet direction can be ignored. The flow is steady and incompressible. Flow is fully developed, therefore variation of velocity profile in x direction is not present. U is equal to U of y. Pressure over any cross section is assumed to be uniform. Pressure can change from one section to other due to friction. P is equal to P of x. The viscous flow is governed by Navier-Stokes equation. X direction mu del square U minus dou P by dou x plus rho g x is equal to rho capital U by capital Et. Finally, substituting del square U and capital U by dt, then removing zero terms, finally we will have mu d square y by dou y square is equal to minus dou p by dou x is equal to 0. Mu do square u by dou y square is equal to dp by dx. Grounding ODE reduced Navier-Stokes equation. U is therefore, since u is equal to u of y and p is equal to p of x. Integrating with respect to y, du by dy is equal to 1 by mu integral dp by dx into dy plus c1. Du by dy is equal to 1 by mu dp by dx into y plus c1. Integrate with respect to y. U is equal to 1 by mu dp by dx into y square by 2 plus c1y plus c2. General solution. Boundary condition: u is equal to 0 at y is equal to 0, u is equal to 0 at y is equal to h. At y is equal to 0, 0 is equal to c2, at y is equal to h, 0 is equal to minus 1 by 4 mu dp by dx into h square by 2 plus c1h. C1 is equal to minus 1 by mu dp by dx into h by 2. U is equal to 1 by mu 4 dp by dx into y square by 2 minus 1 by mu dp by dx into yh by 2. U is equal to 1 by mu dp by dx into y by 2 into y minus h. U is equal to minus h square by 2 mu dou p by dou x into y by h minus y square by h square. at y is equal to h by 2, u is equal to u max. U max is equal to minus h square by 2 mu dp by dx into half minus 1 by 4. U max is equal to minus h square by 8 mu dp by dx. dp by dx. U is equal to 4 u max into y by h minus y square by h square. Velocity profile. Average velocity v is equal to q by a is equal to 1 by a integral u dA is equal to 1 by bh integral 0 to h 4 u max into y by h minus y square by h square into b dy. Integrating 1 by 4 u max by h into y square by 2h minus y cube by 3h square from 0 to h. After substituting, we will get 2 u max by 3. V average is equal to 2 u max by 3. U max is equal to minus h square by 8 mu dp by dx. dp by dx is equal to minus 8 mu u max by h square is equal to minus constant. Above equation shows that pressure gradient is negative constant, hence pressure decreases linearly with respect to x. Hence dp by dx is equal to p2 minus p1 by x2 minus x1. p2 minus p1 by x2 minus x1 is equal to minus 8 mu u max by h square. p1 minus p2 by l is equal to 8 mu u max by h square is equal to 8 mu into 3 by 2 v by h square. Delta p is equal to 12 mu v l by h square. Tau is equal to mu du by dy. Tau is equal to mu into 1 by mu dp by dx y plus c1. dp by dxy plus c1 mu c1 minus h by 2 mu dp by dx into y. Finally, tau is equal to dp by dx into y minus h by 2. For a flow between parallel plates, velocity profile is like this. Shear stress distribution is like this. Tau is equal to dp by dx into y minus h by 2. Y minus h by 2. Initially positive, then negative. Mu is equal to mu du by dy. U is equal to 4 u max into y by h minus y square by h square. V is equal to 2 by 3 u max. Delta p is equal to 12 mu v l by h square. Arrow in shear stress diagram doesn't indicate direction of shear stress at a point because at a time shear stress can have two directions depending upon relative velocity between adjacent layers at that point. The positive or negative shear stress simply indicates whether velocity gradient is positive or negative. Shifting origin at center and indicating vertical Cartesian coordinate by r, we get a relation between y and r. Y is equal to small r plus capital R. U is equal to 4 u max into small r plus capital R by 2r minus small r plus capital R whole square by 2r square. Finally, you will get u max into 1 minus small r square by capital R square. Tau is equal to dp by dx into y minus h by 2. Tau is equal to dp by dx into r. Okay. Cotte flow. Laminar flow between fixed and parallel moving plate. This is fixed, this is moving with velocity v. Cotte flow is governed by Navier-Stokes equation. The assumptions are same. As flow between two fixed plates. The governing equation, reduced Navier-Stokes equation, is also same. The only difference is boundary condition. Governing equation mu d square u by dy square is equal to dp by dx. General solution u is equal to 1 by mu dp by dx y square by 2 plus c1y plus c2. Boundary conditions at y is equal to 0, u is equal to 0, c2 is equal to 0. At y is equal to h, mu u is equal to u. U is equal to 1 by 4 mu dp by dx into h square by 2 plus c1h. c1 is equal to u by h minus h by 2 mu dp by dx. U is equal to 1 by 2 mu dp by dx into y square plus u by h minus h by 2 mu into dp by dx into y. U is equal to u by h into y plus u by h into y plus h minus h square by 2 mu dp by dx into y by h minus y square by h square. In above equation, second term represents velocity profile for laminar flow between two fixed parallel plates. Case 1, if dp by dx is equal to 0, simple Cote flow, then u2 is equal to 0, u is equal to u1 is equal to u by h into y. Velocity profile will be linear. Tau will be constant. Tau is equal to mu u by h. Simple Cote flow. Pressure P is equal to P of I, dP by dx is equal to 0. Case 2, dP by dx case 2 dP by dx less than 0, u2 greater than 0. Then velocity profile is combination of this and this. Then velocity profile will be like this. Here umax at some point velocity profiles. Tau is equal to mu u by h and tau is equal to mu dp by dx is equal to dp by dx into r. Finally, we will get it like this. Tau is equal to tau 1 plus this and this summation. If dp by dx greater than 0, ut less than 0, which means it will be like this. So u is equal to u1 plus u2, superimposition of this, and then we will get it this way. Tau 1 is equal to if mu u by h and tau 2 is equal to dp by dx into r. This will be like this, and this tau is equal to tau 1 plus 2 will be like this. For Cote flow, velocity is maximum either at a point where shear stress is 0 or at top surface. Okay. Turbulent flow, Reynolds experiment. If flow is given, then mixed u naught laminar Re less than 2000, transition 2000 less than Re less than 4000, turbulent Re greater than 4000. Turbulent flow has following characteristics. In turbulent flow, always have heavy mixing present due to mixing flow parameters like temperature, velocity, concentration, velocity are almost uniformly distributed compared to laminar. In turbulent flow, motion of fluid particle is completely random. In turbulent flow, all three components of velocity are present even though overall flow is taking place only in one direction. For example, all direct all dye particles are injected at center, but after some time their position can be away from center. This implies presence of y and z components of velocity. In turbulent flow, velocity at a point continuously changes with respect to time in random fashion about its mean value. Hence, turbulent flows are inherently unsteady. Due to above complexities, turbulent flows are difficult to analyze and we must rely on experimental techniques. Instantaneous velocity, time averaged velocity, fluctuating velocity. Instantaneous velocity u. This is u. Velocity at a point in the turbulent flow continuously changes with respect to time and it is called instantaneous velocity. U time average velocity u bar. It is the average of instantaneous velocity at a point over sufficiently large time interval. It is different from average velocity in the pipe, which is defined as v q by a. V is equal to q by a. U bar is equal to 1 by t integral 0 to t u dt. V bar is equal to 1 by t integral 0 to t v dt. W bar is equal to 1 by t integral 0 to t w dt. F of x integral d f bar is equal to f of x integral f of x dx by b minus a. Fluctuating velocity u prime. This difference. It is difference between instantaneous and time averaged velocity. U prime is equal to u minus u bar. V prime is equal to v minus v bar. W prime is equal to w minus w bar. Time average of fluctuating component must be 0 because fluctuating velocity can be positive or negative, and area above u bar is equal to area below u bar. U prime bar is equal to into 1 by t integral u prime dt. Finally, this is u bar and this is also u bar. It will be equal to 0. U prime bar is equal to 0. Time averaging of continuity and Navier-Stokes equation. Dou u by dou x plus dou u by dou y is equal to 0. After time averaging 1 by t integral 0 to t dou u by dou x into dt plus 1 by t integral 0 to t dou u by dou y into dt is equal to 0. Dou by dou x of then finally dou u bar by dou x plus dou v bar by dou y is equal to 0. Grounding equation can also be averaged over time so that the equation in the form of time averaged velocity can be obtained. 2D, for example, 2D compressible continuity equation can be time averaged as above. Navier-Stokes time averaged equation mu del square u minus dou p by dou x plus rho jx is equal to rho capital Du by capital Dt. Time averaging of Navier-Stokes equation gives additional terms called Reynolds stresses. They are present due to fluctuating components of velocity. Substitute u is equal to u prime plus u bar, v is equal to v prime plus v bar, and w is equal to w prime plus w bar, and average each term with respect to time. After simplification, we will get like this. C in Reynolds is equal to this matrix minus rho u prime whole bar minus rho u prime v prime minus rho u prime w prime everything has bar average, which means average of total average, minus rho u prime v prime u prime minus rho v prime square minus rho v prime w prime minus rho w prime u prime minus rho w prime v prime minus rho w prime square. Turbulent flow over flat plate. Velocity u bar of y, shear stress distribution, it will be like this. Outer layer tau v less than tau r. Overlap layer tau v almost equal to tau r logarithmic. Viscous sublayer linear profile. Tau v greater than tau r, viscous Reynolds. In a turbulent flow, both viscous and Reynolds stresses are present. The turbulent flow region is divided into three parts depending upon relative magnitude of viscous stress tau v and Reynolds stress tau r. Viscous sublayer or laminar sublayer. It is region nearest to the surface where tau r less than tau v. Flow in this region can be treated as laminar flow because velocity fluctuations are negligible. Viscous sublayer is very thin, hence velocity profile inside viscous sublayer can be considered as linear. The thickness of viscous sublayer is given by empirical relation del V is equal to 11.6 by V star. V star is equal to root tau W by rho is equal to shear velocity. V is kinematic viscosity. Overlap layer, it is region next to viscous sublayer where both tau A and tau R have comparable magnitude. Experiments show that velocity profile in overlap layer is logarithmic, which is here. This is logarithmic. Outer layer, it is outermost layer in turbulent flow where tau v is negligible as compared to tau r. The experiments show that shape of velocity profile cannot be predicted in outer layer. For a flow in xy plane, Reynolds shear stress is given by tau r is equal to minus rho u prime v prime whole bar. The fluctuations in velocity are random, hence Reynolds stress is difficult to predict. By Prandtl mixing length theory, Reynolds stress near to surface up to overlap layer is given by tau r is equal to rho L square du bar by dy whole square. In above equation, L mixing length, this represents average transverse distance traveled by fluid particle during mixing before it loses its momentum completely. L is equal to 0.4 y. Near to surface, tau is equal to tau v plus tau r is equal to mu du bar by dy plus rho L square du bar by dy whole square. tau is equal to mu plus rho L square du bar by dy into du bar by dy. Tau is equal to mu plus mu t into du bar by dy. Mu plus mu t is mu effective. The above equation mu t represents turbulent or eddy viscosity. The turbulent viscosity depends on mixing length, which depends upon fluctuations, hence difficult to predict. Mu t is not a property of fluid but depends on flow. Above equation show that due to turbulence effective viscosity is increased. Turbulent flow through circular pipe. Circular pipe. Here till here it is linear, in between it is logarithmic. Tau v, tau r, shear stress, velocity profile, delta v. Turbulent velocity, laminar turbulent velocity profile is inside like this. Laminar velocity profile will be like this. The turbulent pipe flow. In turbulent pipe flow, the thin viscous sublayer is present near to the surface, in which velocity sublayer is linear. In most of the central region, overlap region is present, in which velocity profile is logarithmic. In turbulent pipe flow, outer layer is generally not present. This is because by time overlap, its finished center line is reached. In turbulent pipe flow, shear stress varies linearly with radius. Tau is equal to minus dou p dp by dx into r by 2. The logarithmic profile is almost flat for most of central region, and there is sharp variation in velocity profile velocity near the surface. The turbulent profile is almost flat at center because velocity distributes uniformly due to heavy mixing present in turbulence flow. The logarithmic profile can be approximated as empirical law. By empirical law, u bar is equal to u bar max into 1 minus small r by capital R whole power 1 by 7. The equation of logarithmic profile depends upon nature of pipe surface, that is whether a surface is smooth or rough. Smooth and rough surfaces. Del V, K is less than 0.25 del V smooth. K greater than 6 del V rough. Del Y, if surface irregularities are well submerged inside the viscous sublayer, then surface is treated as smooth, and if surface irregularities protrude outside of viscous sublayer, then surface is treated as rough. Both smooth and rough surface have logarithmic velocity profile in pipe, but equations are different. K is equal to average surface roughness CLA RA. Smooth surface u bar of r by v star is equal to 5.75 log 10 base capital R minus small r small r into v star by v plus 5.5. U bar max by v star is equal to 5.75 log 10 base capital R v star by v is plus 5.5. U max minus u bar of r by v star is equal to 5.75 log 10 base capital R minus capital R by capital R minus small r. Velocity defect law for smooth and rough pipes. V by V star is equal to 5.75 log 10 base capital R V star by V plus 1.75. V is equal to Q by A is equal to integral 0 to capital R U bar into 2 pi R dr by pi capital R square. U bar max by V is equal to 1 plus 1.33 root F. F is equal to Darcy Weisbach friction factor. Rough surface u bar of r by v star is equal to 5.75 log 10 capital R minus small r by k plus 8.5. U bar max by v star is equal to 5.75 log 10 base capital R by k plus 8.5. U max minus u bar of r by v star is equal to 5.75 log 10 capital R by capital R minus small r. V by v star is equal to 5.75 log 10 capital R by k plus 4.75. V is equal to Q by A is equal to 0 to capital R U bar 2 pi R dr by pi R square. U max by V is equal to 1 plus 1.33 root F. F is equal to Darcy Weisbach friction factor. Estimation of wall shear stress tau W in turbulent flow. Tau W is equal to minus dp by dx into capital R by 2. Tau W is equal to mu du by dy. Y is equal to 0 for a linear profile. Tau W is equal to rho v star square. Tau W is equal to f prime by 2 rho v square. Definition of f prime. F prime is equal to fanning friction factor or friction coefficient. Hf is equal to fl v square by 2 gd is equal to 4 f prime lv square by 2 gd. Okay. Flow through pipes, major loss, minor loss, pipe network, series and parallel combination, water hammer, conditions for maximum power transmission. Power systems are used to carry fluid from one location to other. To design a piping system, various losses in system must be known, because some part of power consumed by pump is utilized to overcome various losses. If losses are not known, then pump cannot be selected. In the piping system, the loss due to friction between fluid and pipe surface has typically highest magnitude as compared to other losses, hence it is called major loss. Loss due to friction. All minor losses occur due to flow separation. Orifice meter, flow separation, pipe valve. Major loss experiments show that pressure drop due to friction in pipe depends upon following variables. Delta P is equal to F of L, comma D, comma V, comma rho, comma mu, comma K. By dimensional analysis, above equation can be reduced into dimensionless form as delta P by half rho V square is equal to pi of L by D, comma rho V D by mu, comma K by D. For laminar and turbulent flow through pipe, pressure decreases linearly in the direction of flow. Therefore, there must be linear relation between delta P and L. This implies above equation can be modified as delta P by half rho V square is equal to L by D into pi 1 of rho V D by mu, comma K by D. Delta P is equal to half rho V square into L by D into pi 1 of rho V D by mu, comma K by D. HF is equal to delta P by rho G is equal to pi 1 of rho V D by mu, comma K by D into LV square by 2GD. Comparing with the HF is equal to FLV square by 2GD Darcy-Weisbach equation. For pi 1 of RE is comma K by D is equal to friction factor. Above equation shows that the friction factor for a pipe is not always constant. It is a function of Reynolds number and relative surface roughness. It is also not a property of pipe or pipe material. HF is equal to FLQ by pi by 4 d square whole square by 2GD is equal to FLQ square by 2G into pi by 4 whole square d power 5. HF is equal to FLQ square by 12.1 d power 5 only for circular pipe. Above formula is valid only for circular pipe. For non-circular pipes, head loss should be calculated based upon hydraulic diameter. HF is equal to FLV square by 2GD DH is equal to 4A by P. A is equal to cross-sectional area, P is equal to perimeter. The above hydraulic diameter represents equivalent diameter for non-circular pipe which gives same head loss. It is defined in such a way that dH is equal to D for a circular pipe. Show that fanning friction factor is 1 by 4th of Darcy-Weisbach friction factor. Tau W is equal to F prime by 2 rho V square. Definition of F prime. HF is equal to FLV square by 2GD. Definition of F. Tau W is equal to minus dp by dx into capital R by 2. Tau W is equal to delta p by L into d by 4. F prime by 2 rho V square is equal to rho G hf by L into d by 4. F prime is equal to F by 4. F prime friction coefficient, F friction factor. Show that for laminar flow for circular pipe is F is equal to 64 by RE. HF is equal to FLV square by 2GD. Delta P by rho G is equal to FLV square by 2GD. 32 mu V L by D square by rho G is equal to FLV square by 2GD. Finally, F is equal to 64 by RE. For laminar flow, friction factor is independent of nature of pipe surface and it is completely depends on flow. F is equal to 0.3164 by RE power 0.25 turbulent flow with through smooth pipe K less than 0.25 delta V. 1 by root F is equal to 2 log 10 base R by K plus 1.74 turbulent flow through rough pipe K greater than 6 delta V. 1 by root F is equal to minus 2 log 10 base K by D by 3.7 plus 2.51 by RE root F. Any type of non-laminar flow Colebrook equation. The Colebrook equation is valid for all types of non-laminar flows, transition or turbulent flow through smooth as well as rough pipe at low or high Reynolds number. But this is an implicit nature, hence iterative procedure is required to calculate friction factor. Therefore, the same equation is represented in graphical form and resulting graph is called Moody's diagram. Moody's diagram log 10 base F log 10 base RE. K by D is equal to 0, K by D greater than 0, K by D 2, K by D 3. If in Moody's friction diagram, friction factor versus Reynolds number curves for different values of K by D are plotted on logarithmic scale. Following conclusions are drawn from Moody diagram. For smooth friction factor continuously decreases as for smooth pipe as Reynolds number increases, continuously decreases. For rough pipe, friction factor initially decreases with respect to Reynolds number, but at a higher Reynolds number, it becomes constant. The value of critical Reynolds number after which F becomes constant decreases with respect to relative velocity. As relative surface roughness K by D increases, this critical Reynolds number keeps on decreasing. For a given Reynolds number, friction factor increases at relative for a given Reynolds number, friction factor increases at relative roughness increases as friction. If you draw a line here, as relative roughness increases, friction factor increases. Okay. Minor losses lost due to sudden expansion. V1 here flow separation will be there. When flow enters into larger pipe, it separates at junctions due to its inertia. The recirculating eddies formed due to separation lead to energy loss. The expression for head loss due to sudden expansion can be derived using momentum equation and energy equation. Immediately after junction expansion is not completed, hence velocity at that point is same as velocity in smaller pipe, that is V1. It is obtained that pressure inside separate zone at pressure just before expansion. Therefore, pressure acting on control volume on left hand side is P1. Sigma F bar is equal to m dot V bar out minus m dot V bar in plus dou by dou t of m is P1 A1 minus P2 A2 is equal to m dot V2 minus m dot V1. P1 minus P2 into A2 is equal to m dot into V2 minus V1. P1 minus P2 is equal to rho into V2 square minus V1 V2. P1 by rho g plus V1 square by 2g V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL expansion, head loss due to expansion. HL expansion is equal to P1 minus P2 by rho g plus V1 square minus V2 square by 2g. P1 minus P2, if we substitute this, then finally we will get HL expansion is equal to V1 minus V2 whole square by 2g. Loss due to sudden contraction. When pipe area decreases suddenly, this is vena contracta, the streamlines converge due towards the opening at sharp corner floor separates from the surface. The streamlines keep on converging even in smaller pipe due to inertia of the flow. The section where flow area is minimum is called vena contracta. After vena contracta, flow expands and eddies are formed. It is assumed that losses due to contraction, that is between 1 and C are negligible as compared to losses during expansion between C and 2. The head loss during expansion can be obtained by using formula of sudden expansion between C and 2. HL contraction is equal to HL1 to C plus HL C to 2. This is 0. So HL contraction is equal to VC minus V2 whole square by 2G. HL contraction is equal to VC minus VC by V2 minus 1 whole square. Finally, A2 by AC is 1 by CC. 1 by HL contraction is 1 by CC minus 1 whole square into V2 square by 2G. HL contraction is equal to KL into V2 square by 2G, where KL is equal to 1 by CC minus 1 whole square is equal to loss quotient. CC is equal to AC by A2 quotient of contraction. If contraction quotient value is not given, then head loss should be calculated based on highest value of loss quotient, which is 0.5. From 0.5 it will decrease to 0 A2 based on A2 by A1. Loss at pipe entrance. Sharp entrance KL is equal to 0.5, rounded entrance KL less than 0.5, re-entrant entrance KL greater than 0.5. For rounded entrance, chances of flow separation is less as compared to sharp entrance and KL less than 0.5. KL value depends on relative values of fillet radius and pipe radius. For re-entrant entrance, chances of flow separation is more as compared to sharp entrance, hence KL greater than 0.5. The actual values of KL depends on length of re-entrant and pipe radius. Loss at pipe exiting into reservoir filled with liquid. When a pipe is exiting into reservoir filled with liquid, the Ka of fluid is completely lost after mixing with stationary fluid in reservoir. Therefore, irrespective of shape of pipe exit, entire Ka of fluid will be lost. HL exit is equal to KL V square by 2G. KL is equal to 1. Loss at bend, walls, pipe fittings, etc. HL is equal to KL into V square by 2G. The valve bend orifice material. In all other minor losses, the loss quotient depends on respect to configuration. Example, loss quotient of a wall depends on type of wall and percentage of opening. The loss quotient of bend depends upon relative values of bend radius and pipe radius. Pipe networks. Pipes in series. PA PB equivalent pipe series combination. This is equivalent pipe PA PC PB. If two piping systems are called equivalent with each other, if they behave in similar manner under operating conditions, that is under same end conditions, equivalent pipes deliver same discharge. If pipes are connected in series, then discharge in each pipe remains same. The pressure drop across series combination is equal to sum of pressure drops across each pipe. Q1 is equal to Q2 is equal to Q2 is equal to Q. PA minus PP is equal to PA minus PC plus PC minus PP. HF is equal to HF1 plus HF2. FL square by 12.1 d power 5 is equal to, finally if you cancel constant, FL by d power 5 is equal to F1 L1 by d power 5, d1 power 5 plus F2 L2 by d2 power 5. For n pipes in series, FL by d power 5 is equal to F1 L1 by d1 power 5 plus F2 L2 by d2 power 5, so on, plus Fn Ln by dn power 5. Pipes in parallel combination, PA PB equivalent pipe PA Q1 Q2 PB. When two pipes are connected in parallel, their starting and end points are same, so pressure drop across each pipe is same. The discharge through parallel combination is equal to sum of discharge through two pipes. Q1 plus Q2 is equal to Q. Delta P1 is equal to delta P2 is equal to delta P. HF1 is equal to HF2 is equal to HF. FL F1 L1 Q1 square by 12 d power 5 is equal to FL Q2 L2 square Q2 square by d2 power 5. Q1 is equal to Q into root FL by d power 5 into d root of d1 power 5 by F1 L1. Q2 is equal to Q root of FL by d power 5 into root of d2 power 5 by F2 L2. Final q is equal to q1 plus q2. After cancelling q, root of d power 5 by fl is equal to root of d1 power 5 by fn l1 plus root of d2 power 5 by f2 l2. For n pipes in parallel, root of d power 5 by fl is equal to root of d1 power 5 by f1 l1 plus root of d2 power 5 by f2 l2, so on root of dn power 5 by fn ln. Total energy line, hydraulic gradient line. Flows through like this. So this is hydraulic gradient line. Above that, this is total energy line. This is V exit square by 2g. Both start here. It will start here. It total energy line or total energy line or energy gradient line. It represents variation of total energy of fluid. P by rho g plus v square by 2g plus z in direction of flow. It is obtained by subtracting various losses from initial energy of fluid. In a pipe of constant diameter, TEL decreases linearly because head loss HF is directly proportional to length. In a pipe of variable diameter, slope of TEL is not constant. Magnitude of slope is equal to fq square by 12.1 d power 5. Hydraulic gradient line, it represents variation of piezometric head P by rho g plus Z in direction of flow. It is obtained by subtracting Ke head from Te head. It in a pipe of constant diameter, TEL and HGL are parallel since velocity is constant. TEL always fall in direction of flow, but HGL may fall or rise depending on whether velocity is decreasing or increasing. Water hammer, water hammer. This high pressure V is equal to 0, increased diameter, C is equal to sonic speed in fluid. When valve is suddenly closed, pressure in the vicinity of valve increases due to inertia of flowing fluid. Due to increase in pressure, liquid gets compressed and pipe gets expanded. The extra space created can further occupy some of incoming liquid. Hence, entire liquid in the pipe is not stopped suddenly. As fluid is stopped layer by layer, interface between high pressure fluid and low pressure fluid travels upstream. Speed of interface is equal to speed of sound in fluid. When pressure wave reaches to entrance of pipe, high pressure liquid flows back into pipe to release the pressure. This causes reflection of pressure wave. After multiple reflections, intensity of pressure wave vanishes. The first wave has highest intensity of pressure wave, cause damage to the piping system, and so water hammer should be avoided. To avoid water hammer, the valve should be closed gradually. Such tank is to be provided on upstream side of valve to release the pressure. Pressure rise due to water hammer, sudden closure of valve, TC less than 2L by C, and pipe assumed to be rigid. Area A, length L, V low pressure, high pressure V is equal to 0. When fluid is flowing in the pipe, it has Ke is equal to half mv square. After some time, velocity in pipe becomes 0 everywhere. The Ke of fluid is converted into strain energy of compressed fluid. Initial Ke is equal to final strain energy. Half mv square is equal to half sv square by K into V bar. Can rho V bar cancelled. Then delta P square is equal to rho K V square. Delta V square is equal to rho square K by rho V square. Finally, delta P is equal to rho CV. C is equal to root K by rho. C sonic speed. V is equal to flow velocity. Rho is equal to fluid density. Case 2, sudden closure of valve, TC less than 2L by C and pipe is assumed to be elastic. Delta P is equal to rho C prime V. When pipe is elastic, some part of in the initial kinetic energy is absorbed by pipe in the form of strain energy. Therefore, pressure rise in case of elastic pipe is less as compared to rigid pipe. Delta P is equal to rho C prime V. C prime is equal to root K prime by rho. D is equal to pipe diameter. T is equal to pipe thickness. E is equal to Young's modulus of pipe. V is equal to Poisson's ratio of pipe. 1 by K prime is equal to 1 by K plus D by T into 5 minus 4V by 4. 1 by K prime is equal for steel and cast irons. V is equal to 0.25. 1 by K prime is equal to 1 by K plus D by T. Case 3, gradual closure of pipe T greater than 2L by C. When valve is closed gradually, K is not converted into strain energy because by the time valve is closed, reflected low pressure wave will reach the valve. It is assumed that entire liquid in pipe is retarded to final velocity 0 with constant retardation, and force required for retardation is provided by pressure increase to near to the valve. V delta P V is equal to 0. Retardation V is equal to V minus 0 by Tc. Force is equal to delta P A into A. Delta P into A is equal to mv by Tc. Delta P into A is equal to rho A L into V by Tc. Delta P is equal to rho V L by Tc. Conditions for maximum power transmission through pipes. Capital H is equal to V square by 2G plus HF. Power is transmitted from the pipe in the form of Ke. Power transmitted is given by half m dot V square is equal to rho Q V square by 2G into G is equal to rho Q G into capital H minus HF. Power is equal to rho G Q into capital H minus FLQ square by 12.1 D power 5. For maximum power transmission, d by dq of rho g q into h minus fl q square by 12.1 d power 5 is equal to 0. H minus capital H minus 3 fl q square by 12.1 d power 5 is equal to 0. Capital H minus 3 hf is equal to 0. Hf is equal to h capital H by 3. Power transmitted is not maximum when hf is equal to 0 because head loss is 0 only when discharge through pipe is 0. In that case, power transmitted is also 0. So maximum power transmitted when hf is equal to capital H by 3.